Today on How It's Made. Motion sensors. Belt loaders. Pheasant breeding. And diving helmets. Tiny motion sensors, known as accelerometers, are at the heart of much of today's technology. Built into a smartphone, for example, the sensor detects both movement and the angle at which the phone is being held to trigger the rotation of the screen. This little chip is why a smartphone knows when it has moved. These motion sensors are tiny but smart because they can detect every move. They start with silicon discs called wafers. Each wafer will be used to make thousands of motion sensors. A technician aligns the discs in a cassette, using the flat part of each one as a reference point. Once properly aligned, a mechanism lowers the silicon wafers onto a carrier made of quartz, which can withstand intense heat. The technician loads the wafers into the furnace. Inside, the 2,000-degree heat and steam cause an oxide to form on the surface of each wafer. It'll act as an electrical insulator. Then it goes into what's known as a sputter system. Here, inert gas ions bombard aluminum, causing it to sputter onto the wafer until an even layer accumulates. This aluminum layer will serve as a conductor of electricity. The next machine deposits a light-sensitive chemical onto the wafer. The wafer spins, allowing the chemical to flow evenly across the surface. This all happens under the glow of yellow light. To prevent the untimely activation of the chemical, which reacts to bright light, just like an unexposed photographic negative would. They're now ready for that bright light. UV light beams through tiny patterns on a glass plate to activate the light-sensitive chemical. The patterns transfer to the wafer surface, forming an outline for thousands of motion sensors. Another chemical then flows onto the silicon wafer to further develop these minuscule images. Next, lasers locate the wafer's flat edge, signaling a chuck to spin into its proper position for plasma etching. The etching creates thousands of free-moving 3D structures. Each one is a motion sensor. After etching, a sprayer blasts the surface with carbon dioxide. It's the only way to clean it without damaging the now movable sensors. At the next station, a robotic arm flips the wafer into position. A tray moves under the robot and places the wafer on it. The tray retracts and loads the wafer into a clamping system. It then collects a second silicon wafer and places it on the first one in the clamp. The second wafer acts as a lid to protect the individual sensors. Held in the clamp, a machine heat seals the two wafers, and the bond is complete. Next, a computerized saw cuts grooves into the top wafer only, while a steady stream of water keeps the dust down. The saw exposes the aluminum layer on the bottom wafer, something that will allow each sensor to make an electrical connection. A platform now moves the wafer a millimeter at a time, so that a probe can test each sensor and confirm it performs correctly. This continues until every sensor on the wafer has been tested. From a plain silicon wafer to a unit that contains thousands of motion sensors, this process takes 3 weeks. After the individual sensors have been cut and encased in plastic, they're ready for a final test. A robot loads each sensor into a test socket. The socket both tests the sensor's performance and programs it to customer specifications. A robot packages the sensors for shipping. And once installed in phones, tablets, and computers, these motion sensors will be ready for action. If you've been to an airport, you've seen mobile belt loaders on the tarmac. They drive from the terminal to the aircraft, align their built-in conveyor belt with the entrance to the cargo hold, then load baggage or cargo on board. When an aircraft arrives, they do all that in reverse to unload baggage or cargo. A turn of the control handle adjusts the height of the front of the belt loader, enabling it to reach the cargo hold of even the tallest aircraft. The rear height is also adjustable, so the airport baggage handlers can set it at a level comfortable for loading. The vehicle and the conveyor belt are separate units. In this part of the factory, workers construct the conveyor's steel frame. They weld together all the steel parts, then grind all the weld seams flat so that the belt will move over the frame smoothly. Workers install a crossmember just past the midpoint of the frame. It will connect with two sets of lift arms installed in the vehicle, one which raises and lowers the front of the conveyor, the other which raises and lowers the rear. Workers insert alignment pins to position the crossmember on the frame correctly, then weld it into place. The vehicle's chassis is also made of welded steel. Workers blast the chassis and conveyor frame with a metal abrasive. This removes rust and other debris, prepping the surface for paint to adhere properly. They caulk all the unwelded seams to prevent corrosion, then spray a coat of primer, followed by a coat of industrial-grade paint in the color the customer requested. Once the paint dries, assembly can resume. On the conveyor frame, they install the motor which drives the belt. There are two options available: this hydraulic motor powered by the vehicle's engine, or an electric motor powered by battery. The motor rotates two large metal rollers, one at the front of the frame, the other at the rear. The belt wraps around these rollers so that when they turn, the belt moves. Between the end rollers, running the entire length of the conveyor, workers install 58 smaller metal rollers. These form the floor of the conveyor and can support up to a ton of cargo. The motor runs these rollers forward or in reverse, depending on whether the belt is loading or unloading the aircraft. The belt itself is made of high-strength tire-grade rubber with an anti-skid texture on the surface. To be long enough to loop around the 25-foot-long conveyor, plus the end rollers, the belt is 50 feet in length. The ends have teeth, which fit into each other like a zipper and fasten with a metal pin. Elsewhere in the factory, technicians install components on the vehicle chassis. First, the front and rear axles. Then, on each axle, two wheels, with tires specifically designed for long life on the airport tarmac. At the rear of the chassis, they install the hydraulic cylinder, which raises and lowers the rear lift arms. Then the vehicle's engine, which can be either gas, diesel, propane, or electric powered. The vehicle drives at a maximum speed of just 25 miles per hour, but that's more than sufficient for traveling between the terminal and the aircraft. After installing the power steering system, technicians run wiring for the lights and other electrical components, run hydraulic hoses for the brakes and lift cylinders, and install the controls for the conveyor. They install the hydraulic cylinder which raises the front lift arms, then connect the fluid hoses to the hydraulic pump. Next, they install the front and rear lift arms along with a safety brace underneath to use when mechanics are working beneath the conveyor. They attach the lift arms to the front and rear cylinders, which expand to raise the arms and retract to lower them. Now, workers hoist the conveyor over the vehicle and bolt the front and rear lift arms to the crossmember on the conveyor's underside. The two units are now one mobile belt loader, ready to roll off the line and hit the tarmac. The pheasant is one of the most sought-after game birds in North America, but populations in the wild have dwindled. To replenish them and also supply a market for pheasant meat, farmers raise breeding stock and incubate their eggs to make it more likely they'll yield chicks. With stunning plumage and an ability to both run and fly, no wonder the pheasant struts around. Each pheasant lays approximately 4 eggs weekly, April through to July. Farm workers collect the eggs daily before the pheasants have an opportunity to nest. With their intervention, the hatch rate will get a big boost. It will go from 40% to at least 75%. The farmer washes the eggs in water and special soap to remove dirt and bacteria that could infiltrate the shells and harm the growing chicks. She inspects the eggs and rejects any cracked or very large ones that would contain a double yolk. Eggs with cracks or double yolks won't hatch. One last dip, and she sets the eggs aside to drip dry. Once dry, she taps eggs together systematically and listens. If the tap sounds like fine china clinking together, they're suitable for hatching. But if the tap sounds dull, there's likely a crack. By listening, she finds 1 or 2 cracked eggs she missed with a visual inspection. She places the eggs in an incubator rack and transfers it to a cooling room. The pheasant eggs chill here for a few days. The cooling slows down cell division until the farmer is ready to put the eggs in the incubator. Chick production is timed for 2 hatches weekly. When the time is right, she transfers the eggs to the incubator. The incubator is at toasty 100 degrees Fahrenheit to mimic the warmth of a hen's body. She latches the racks onto an automated system that gently rocks the long cradles back and forth to turn the pheasant eggs. Turning the eggs routinely is something that nesting hens do naturally, and it's important. Without it, the developing embryo could stick to the shell, causing abnormal growth. The farmer monitors the incubator temperature and humidity several times daily. 3 weeks later, she removes the rack and places it on a tray lined with cheesecloth. She opens each cradle, and the eggs spill softly onto the tray. At this point, there are tiny pits on the shells, caused by the chicks' beaks as they attempt to break through. Once on the tray, she arranges them close together in a figure-8 configuration. This way, the chicks can feel each other moving, cueing them to break out of their shells. She pumps water onto the tiers of the hatcher now. The hatcher is warmer than the incubator. She covers the trays with screens to keep the chicks from jumping onto other trays. As the water heats up, the humidity increases. This causes the shells to weaken, making it easier for the pheasant chicks to break out of their shells. After a couple of days, the eggs have hatched. After drying off, the chicks are fluffy and lively. The farmer packs them in ventilated cardboard boxes. Freshly hatched, they'll survive 60 hours without food, giving the breeder enough time to ship them anywhere in the world. That's why pheasants are easier to ship when they're chicks. Some customers prefer more mature birds, so the farmer raises some chicks in wire frames for a week until their legs become stronger. Then they move those chicks to other heated buildings until they're ready to thrive outdoors. Some will be kept as breeding stock. Others will be sold as food. The rest will be introduced into the wild and just fly away. Today's diving helmets are produced primarily for history buffs and divers performing underwater work, such as welding the submerged parts of bridges. Unlike a scuba tank, which carries a limited amount of oxygen, a helmet connects to an air pump at the surface, providing an unlimited air supply. A diving helmet is completely watertight, so the diver doesn't need a mouthpiece to breathe and can speak to people at the surface via a built-in transceiver. This helmet is the design the U.S. Navy used from 1916 until 1984. At the factory, they make the helmet's head portion, called the bonnet, from a copper sheet about 1.5 millimeters thick that's been spun on a lathe into a dome. They buff it smooth, then using a template, mark where to cut openings for the various components. It takes a good 1.5 months for the factory to machine all those components and assemble the helmet. With a hammer and punch, they dimple the copper at the marked spots. This will give the saw a foothold on the otherwise slippery surface. Then they apply cutting oil to prevent the saw from overheating as it bores through the metal. The first cut is a 6-inch wide hole at the front for the bonnet's hinged faceplate. They saw 8 openings for the bonnet's other components, including 3 windows. Next, with tin and lead solder, they fuse a threaded neck ring to the bottom edge. This ring attaches the bonnet to the helmet's breastplate, which bolts to the collar of the diver's dry suit. Then they solder a base to the faceplate opening. Like all the helmet's components, it's made of red brass, which is more durable than standard brass due to its higher copper content. Next, through a template, they drill holes into a banana-shaped brass exhaust tube. It enables the diver's exhaled air to exit the helmet. They solder the exhaust to the bonnet, positioning the non-perforated end over a hole near the diver's mouth and the perforated end at the rear. This directs air bubbles behind the diver, so as not to obstruct the view. Then they solder on the remaining components, including 3 window bases. Just as one does when installing a window in a building, they apply glazing to the faceplate and window bases to seal the 3-inch thick acrylic pane against leaks. For underwater safety, they screw a brass guard to the base. This prevents the pane from popping out should too much air pressure build up inside the helmet. Now they install the transceiver and feed its wires through a brass elbow, which will ultimately attach to a communications cable running to the surface. With the bonnet complete, it's time to shape the helmet's breastplate. They lay a copper sheet onto a breastplate-shaped mandrel, clamp on a breastplate-shaped form, heat the copper with a torch to make it malleable. Then, with a wooden mallet soaked in brine to keep it from splitting, pound the copper for about 45 minutes until it assumes the shape. Then they chisel out the neck opening. Once the copper has cooled, they transfer the breastplate to a form and begin reinforcing the bottom with a brass strap. After clamping the strap in position, they hammer the copper around and over its outer edge. Then they remove the clamps and solder the copper to the strap. Once the soldering's done, they grind the surface smooth and drill 12 holes into the strap for the custom-made bolts that connect the helmet to the collar of the diver's dry suit. Then, after flipping the breastplate upside down, they wrap solder around the bolts, drop them in the holes, and melt the solder to lock them in. They polish the metal and solder on the last breastplate components, a threaded neck ring for connecting the bonnet, and, at the front, a pair of brass eyes for lashing the air and communication hoses off to the side, so they won't get in the diver's way underwater. If you have any comments about the show, or if you'd like to suggest topics for future shows, drop us a line at sciencechannel.com/howitsmade.